This video serves as an introduction to the concept of a power series. So we'll start with a definition of what a power series actually is. A power series is a series starting at n equals 0 and going to infinity of a set of coefficients times different powers of x. Now we're going to assume that when plugging in n equals 0, regardless of the value of x, then raised to the 0 we're going to get 1. So this takes the form of a constant term plus an x term plus an x squared term plus an x to the third term, and so forth and so on. So each of those c's represents the coefficient of x raised to the corresponding power. Now this is a specific kind of power series, and I'll explain with another definition. So this is the more generic form of a power series, like so. Now with that in mind, this would look like, once again, a constant term plus an x minus a term plus an x minus a squared term plus an x minus a to the third term, and so forth and so on. Now once again, in this case, c sub I is referring to the coefficient of whatever's being raised to the ith power. In this case, we refer to this as a power series centered at x equals a. We refer to it as a power series centered at x equals a because if I were to plug in x equals a, I would get that all of these terms would cancel out. Now, one of the big questions we're going to be posing in this section is, for what values of x will the power series converge? For what values of x will the power series converge? Now with that in mind, there are three possibilities. Now, regardless of which one of these kinds of power series we're dealing with, a power series will always converge at its center. Because if I were to plug in the center of x equals a, I would get c naught plus every term thereafter would become 0. Because we actually get a number out of that, c0, we say that it would converge. Now the first kind of power series that we had would be technically considered a power series centered at x equals 0. So if I were to plug in x equals 0, I would get, once again, c0 plus a lot of terms that wind up being 0. So the three possibilities for where the value of x, or for what values of x the power series will converge, converges at just its center. Another possibility is it converges for all real numbers. That is, plug in any value for x and it still converges. The third possibility is that it converges for only numbers within a certain distance of x equals a. That is to say, in the third possibility, if we were to consider x equals a, then only numbers within a certain distance of x equals a would this converge. This is going to produce what's known as an interval of convergence. An interval of convergence. Now it doesn't necessarily look like it, but Since we're extending a certain distance in either direction, we refer to that distance as a radius of convergence. Now with that in mind, when it comes to a radius of convergence, we typically refer to this value as capital R. Now, in addition to all of the numbers within a certain distance, we have to pose the question of whether or not it will converge at the endpoints of the interval. So that value R is referred to as a radius of convergence. Now, in each of these three cases, we have a particular radius associated with this. If it converges only at the number itself, what we're essentially saying is that the radius of the interval is 0. Starting at A, we extend 0 units to the left and to the right. If it converges for all real numbers, we're essentially saying that the radius is equal to infinity, because it will extend infinitely in both directions. And in the last case, we wind up with some finite value of R. In all three of these cases, it is going to be necessary to do a couple of things. So to find radius and interval of convergence for a given power series, first thing we'll do is apply either the ratio or the root test. I'm going to say probably 9 times out of 10 you're going to want to go with the ratio test. There is a very specific case in which you want to do the root test, and that's when everything is raised to an nth power. You'll notice back in the original definition, the x was already being raised to a power, so it works exceptionally well with both the ratio and the root test. Whether you apply the ratio or the root test is going to depend on your coefficients c sub n. This is going to set up an inequality. So regardless of whether you're using the ratio test or the root test, you'll be taking the limit as n goes to infinity. For the ratio test, it'll be a sub n plus 1 over a sub n. Or for the root test, you would be setting up the limit as n approaches infinity of the nth root of the absolute value of a sub n. And in either case, you're going to get some expression. This expression is going to be a function of x. Now, there are some possibilities where all of the x's vanish, and we'll cover those at a later point in time. The inequality that we're going to be setting up is the fact that if this value is less than 1, it is guaranteed to converge. However, if it's equal to 1, it might converge. This is that little uncertainty that we had about the endpoints of the interval. So solve this inequality. For x. Now, in the event that the x has vanished for this and we have just a number, then you'll be able to draw a conclusion about whether it converges for all real numbers x or at just x equals a. Otherwise, chances are pretty good you are going to get something of the form x is between a minus r and a plus r, whatever numbers those happen to be. And we also have the possibility that it could converge at the two endpoints. So with that in mind, we are also going to test the convergence at the endpoints. And by that, I mean go back to the original series. So plug in the endpoints to test for convergence. And by test for convergence, I mean apply all of the tests that we've done thus far, the alternating series test, the integral test, the direct comparison test, the limit comparison test, one of those tests to see if it converges. After you've done that, your final answer will be an interval and a radius. If it converges at an endpoint, then we want to include that endpoint. So we would use something like the square brackets on our interval. If it diverges at an endpoint, then we would indicate with parentheses. So ultimately there are going to be a total of 4 possibilities for these intervals of convergence. It could be completely closed, it could be half closed, half open, it could be half open, half closed, or it could be completely open. We'll investigate with some examples in the next video.